Hello everyone, welcome. This is Steve Suffoletto from Erie Community College, just south of Buffalo, New York. Today's presentation is going to discuss the basics of halftone screening. The purpose is most traditional or analog printing processes can only print binary images, meaning they can only print image areas with ink or non-image areas with no ink. Therefore, they're binary. Now, halftones are a binary representation that has been converted from the original continuous tone image. This halftone illusion is accomplished by screening with different size or area of dots. While this topic is mostly for pre-press, the press room must also know and understand the concepts in order to match the proof. Now, there's two types of images, or photographs or pictures. We have continuous tone and we have halftones. Continuous tone can be abbreviated contone or CT, and halftone can be abbreviated HT. So continuous tones are the original. They can be analog, and typically they are film photography. The halftone is the reproduction. It's digital, and it's printing. Prepress has the grayscale, which gets converted into pixels, and the press room has the raster, which gets converted into a bitmap, which gets converted into a dot. So the image on the left is continuous tone, and its tone curve would look smooth. It would have a ramp with a steady incline on it. The image to the right is the halftone, and its tone reproduction curve would be very discrete. It would have some intervals and steps or stair-stepping. So halftone screening takes a photograph or a picture and converts it into dots or spots. Now, if they're large, they're called dots for AM amplitude modulation. And if they're smaller, they're called spots for frequency modulation or FM. And it's actually a technology that is a combination of both called XM for cross modulation. It's a hybrid technology. So if we're using AM, all halftones have four characteristics or attributes. They are size, ruling, angle, and shape. So when we talk about size, it's a percent area. If there's nothing there, it's 0. If everything is there, it's 100% solid. And halfway between nothing and all, or halfway between 0 and 100, is 50%. When it comes to the ruling, it's often called screen count or line screen or frequency or spacing. It's typically measured in lines per inch, LPI. And for the angle is measured in degrees, rotational degrees. A one-color black and white halftone would be 45. A two-color duotone, the black would be at 45. And when we have more than one angle, we have to be concerned about interference patterns, which are called moires, which are bad, or rosettes, which are acceptable and okay. And then the fourth characteristic is the geometry or the shape. We can have a round circular dot, we can have a square dot, or we can have an elliptical chain dot. Let's talk more about the size of the dot. We have three areas of interest: the highlights, the midtones, and the shadows. So the highlights are the light colors. Some people call these pastels or tints. They're somewhere between 0 and 10%. So that's an example of a highlight dot. The midtones are the grays. They're middle and medium. They go somewhere between 40 and 60%. Obviously, 50% would be perfect symmetry. Half is black, half is white. And when we get into the shadows, we're talking about the dark black colors. That's somewhere between 90 to 100%, and that would be an example of the shadows. So we go from 0 paper to 100% solid black ink, and that's your tonal scale. This image on the right is a blend or a vignette or a gradation. The important thing to remember here is as the size of the dot changes, your tone changes, or your lightness darkness changes, or your density changes. The larger the dot, the darker. The smaller the dot, the lighter. We can also add a quarter tone, 25%, and a 3/4 tone, 75%. In our laboratory, we will print 3 projects, one for highlights, one for midtones, and one for shadows. Frankenstein is the highlights, Dracula is the midtones, and the Mummy is the shadows. Let's look at tone reproduction, or TR. So we're going to build a graph or a chart here. The horizontal x-axis is percent dot size area, going from 0 to 100, going from bare paper to solid ink. The vertical column to the left, or the y-axis, will be the density. D for density, D for darkness, it's the tone. So at the bottom is 0, which is white or light, and at the top is black, which is dark, and we'll max out at 2.0. So if we measure the density of the dots, you get a curve here, and that curve is bent. It's curved, it's not a straight line. And if you're printing on uncoated or plain paper, you typically will max out or D-max at 1.25. If you print on a higher quality paper that's coated and gloss coated, your maximum density or D-max will be more like 1.70. The eye is the most sensitive to the highlights. So for tone reproduction, we want to make sure that this area is faithful and accurate to the original, almost a straight line portion. It's not until you get into the darker shadows that we start to bend this curve. The eye is less sensitive, more forgiving in the dark shadows. Again, as the dot changes its size, you change the density. So if you want to control the color, you have to control the size of the dot. As the dot gets larger, the color gets darker. As the dot gets smaller, the color gets lighter. So for image quality, the brightness, the contrast, and the detail is controlled by the size of the dot. Unfortunately, the press room and the press operator on press has very little control over the size of the dot. They set their water balance, they set their ink to get the proper density, they check their pressures, and they basically are trying to get consistency in printing. Let's look at dot gain as it goes through the reproduction process. Again, dot gain is called tone value increase, or TVI. So if I have a 50% dot in the file, and I now make a negative on a image setter, which has been linearized, meaning a 50 is a 50, that dot from file to negative will remain a 50, so there's no change in dot size area. If I now make a plate, and that plate is made in a vacuum contact frame, that's analog plate making, the negative dot on the plate will increase by 4%, so the total size of the dot is now 54%. Now if I make digital plates with a plate setter, CTP, computer to plate, that is typically also linearized. So that would be the same condition previously as the film image setter. There would be no change in size of the dot. Now we take that plate and we put it on press and we ink that plate. Some of the ink is going to fall over the edge of the dot. So there is going to be some gain or growth, probably about 5%. So now the dot is a 55. You take that ink on the plate and you squeeze it against the blanket under pressure, and it's now going to grow maybe another 2% for a total of 7%. So the total dot gain is 57%. Take that inked dot on the blanket and now really squeeze it hard onto the paper against the impression back cylinder, and that dot is going to grow maybe a total of 16%. So the dot will now measure 66%. So if you measure the area 66% on paper and you reference and compare that back to the original, the file at 50%, 66 minus 50 is 16% dot gain. Now, while there is dot gain from physical mechanical pressures, there's also dot gain from how light reacts with the ink in the paper. Some of the light is going to get trapped under the dot and inside the paper, making it look to the densitometer like there's less light, more density, therefore larger dot size area, therefore more dot gain. So in an advanced class, we would have to have a technical conversation about the different types of dot gain, whether it's mechanical or physical or optical, using the Murray-Davies formula or the Yule-Nielsen formula. Let's take another look at the dot gain graph. Again, on the bottom, we have dot size area increasing from left to right. And on the vertical column, we have dot gain increasing from bottom to top. And we typically get a curve that looks like this. Now, that curve has a shape, kind of like a mountain or a hill, a bell. It has a center, that's the peak or the mode. And it has a height, the amount or the magnitude. So this is typical for sheet-fed offset lithography and cold set and heat set web offset lithography. The most amount of dot occurs where there's the most amount of perimeter, border, or circumference, and that will be at 50%. Now the green curve might be coated paper, only at 15 or 16% dot gain, and the red curve might be the same process, but printing on an uncoated regular piece of paper. Now, special note here, if this was flexography or flexo, this curve shape would skew and shift to the left giving you more dot gain in the highlight areas. If you follow ISO 12647-2, the target expectation is 16% for dot gain with a tolerance of plus or minus 4%. Ideal Alliance's GRACOL, G-R-A-C-O-L, General Requirements for the Applications of Commercial Offset Lithography using the G7 calibration method, expects to have a density of 0.60 at the 50%. The second characteristic of halftone dots is their screen ruling, measured in lines per inch or LPI. Now, the whole goal and objective of halftoning or screening is to make the image look continuous tone. So this is going to depend on the paper, the ink, the printing process, and the viewing distance. A typical viewing distance, when you read a newspaper or a magazine or a brochure, you have your bent elbows, arms, that's about 18 inches from image to your eye. We can categorize the screen rulings into coarse, medium, and fine. Coarse screen rulings are 100 or less, 85 lines per inch. So newspapers typically are 85, 100, and 110 LPI. They follow the SNAP recommendations, SNAP specifications for newspaper advertising production. Then medium screen rulings would be magazines using SWOP, SWOP specifications for web offset publication, or again, GRACOL for commercial printing. LPIs here are 133, 150, and 175. I remember in my early career days back in the 70s, we were at 133, and then in the 90s, we were at 150, and now in the 2020s, almost everybody's at 175 LPI. So over time, we've seen the screen rulings increase. This is especially true in flexography because they've been able to reduce the size of their min dot, their minimum dot, which allows them to print at higher LPIs. And then the other category of screen ruling would be fine. This is probably 200 or above. So some people call this high line or ultra fine. At this point, you might want to consider getting away from AM and going to FM frequency modulation or XM cross modulation hybrid. We can say this, however, the finer the screen ruling, typically the more detail you will record. However, the finer the screen ruling, the smaller the dot, and the closer together they are, this can cause other technical problems or print quality problems. We don't want that screens to plug up or fill in or have bridging or other types of problems. Here's an example of a 50, 100, and 150 LPI at 10x magnification. These are actual photomicrographs or microphotographs of a film negative on a light table. You can see that as you increase the LPI, the dots get smaller and they get closer together. Here's the same illustration, but now at 40x. Again, as the LPI increases, the dots get smaller and they get closer together. The third characteristic of a halftone is the screen angle, the rotation, and measured in degrees. For halftones, we always want the black to be at 45 degrees because your eye will recognize patterns that are vertical or horizontal at 0 or 90 degree orientation, because your brain recognizes patterns from left to right, top to bottom, because of how you read. When we get into duotones, we want the duotone black to be at 45. The second color, the spot color, can be at 0 or 90. And we want to avoid any interference patterns. For process color printing, full color printing, we have a bit of a challenge here because we're running out of angles. So with cyan, magenta, yellow, and black, CMYK, black is the darkest color. It gives you the most contrast against white paper. We'll put that at 45 degrees, just like we would do for a duotone or a halftone. Then if you take 90 degrees and divide it by 3 other colors, you get 30 degrees of rotation. 45 plus 30 would give you 75, and 45 minus 30 would give you 15. Now, 75 plus 30 would be 105, but you have to realize once you pass 90, you're repeating again. So 105 minus 90 is 15 degrees. So the problem is we ran out of screen angles because we got too many colors. So yellow is the lightest color. What we'll do is we'll cheat with it and we'll put it at a half angle. Half of 30 would be 15 degrees. So 75 plus 15 would be 90 degrees. So to help not see a moire at yellow 90 degrees, we often output at a higher, finer LPI. Now just imagine if we went to extended color gamut or ECG and we added 3 more colors, an orange, a green, and a violet, an OGV, where do we put what angles do we use for those new colors? Well, typically you're going to use angles that are complementary or opposite across from them. So the opposite of a green would be a magenta, the opposite of an orange might be a cyan or a bluish, the opposite of violet might be a yellowish. Continuing our conversation with screen patterns, when you have more than one color, you have more than one angle, and you can get an interference pattern. Now, a rosette is an interference pattern, however, it's acceptable. And it's called a rosette because under magnification, the pattern looks like the petals of a rose. Now, the center of that rosette may be hollow, white, clear, or it could be solid. A moire is an unacceptable pattern that we don't want, so it has that cross-hatch pattern to it. It could be caused by the additional color and its angle, or it could be caused by a pattern in the original image. That would be called an object moire. In lab, the project we will be printing for screen angles will be the duotone. And the fourth characteristic for dots is shape. So we're going to talk about the geometry and how many edges touch. So a square has 4 sides, 4 corners, and at 50%, all 4 corners touch. The problem is when you're at 48, no edges touch, and then 2% more from 48 to 50, suddenly all 4 edges touch. You get a sudden, abrupt change in density. We call this dot gain jump or dot gain bump. Of course, the pattern you get here is the familiar checkerboard pattern. So it's very easy to identify a square dot shape because of the checkerboard pattern. If you go to a round circular dot, no edges touch at 50%. It's not until that dot becomes a 68% that the edges start to touch. And now what you start to see is what looks like a diamond. And because the dots don't touch until 68%, you're spreading the amount of dot gain over a longer area. So printing processes or substrates that have a lot of inherent dot gain in them typically will use a round dot, like newspaper printing on groundwood newsprint paper. Another geometric shape dot we can use is called the ellipse or elliptical. 2 edges touch at 40%, and then the other 2 edges touch at 60%. So it looks like a link on a chain or a chain link. Again, this spreads out the dot gain over 20% from 40 to 60. And the third dot shape is called Euclidean. And what happens here is the dot changes its shape when it goes from the highlight to the midtone to the shadow. It's a round dot in highlights and shadows, but at the midtone, it's a square dot. The lab project we will print for dot shape will be Elvis. And some basic history on halftone screening. You know, prior to photography, 1839, you couldn't print a halftone. Everything was a line engraving, either in wood or metal. So an artist had to carve or engrave or draw the illustration to look like a photograph. Then, when photography was invented, we could use a glass cross-line screen. This was between the lens and the film. And then Kodak in 1942 invented the gray and magenta film contact screens that you placed right on top of the film. And the 3 basic exposures for making high-quality halftones would be the main exposure. It placed the highlight dot. The flash exposure, it placed the shadow dot. And the bump or the no screen exposure, which changed the midtone location to compensate for dot gain. And then in 1974, Hell came out with their Chromograph DC300 drum scanner, and now we never use contact screens anymore. We were generating the dots electronically. This was called an EDG for electronic dot generation. This eliminated contact screens. In summary, halftones need proper tonality and contrast to look good. 3 areas of concern are the highlights, the midtones, and the shadows, abbreviated H, M, and S. The type of paper, uncoated versus coated, will affect the solid ink density, SID or SID, which affects the tone value increase, TVI. And screening can be done with dots, amplitude modulation, AM, or it can be done with spots, frequency modulation, or we could do it with a combination of both, and that would be called XM, cross-modulation, or hybrid. If AM, all dots will have a size, a spacing, a shape, and an angle. I do have some previous posted YouTube videos that are related to this topic. One is titled Image equals Solid plus Screens. Another is called Tonal Metrics Table. And the third one is called Resolution, Pixel Spots, and Dots. As always, thank you very much. I appreciate your attendance, your time, and participation. Hopefully you found this presentation interesting, informative, and relevant. And please provide feedback with a thumbs up. Until we meet again, have a good day. Bye now.